Well, another model that would generate a system of differential equations would be species competition. And this would be the way animals behave if they're competing for the same prey. For example, if there are two species that don't eat each other, but they share the prey, like foxes and coyotes, all eating rabbits, or bobcats and lynx, all eating, I hate to pick on rabbits, but it seems like rabbits. Or it could be rabbits and groundhogs eating the same prey. Their prey, of course, would be maybe something like broadleaf plantain, which is a plant that grows in people's yards, and one of the things that bunnies as well as groundhogs like to feed on. So,
I want to discuss all this behavior.
Well, that's what we're going to do. So, assume that both grow according to the exponential model. Change in population over time is proportional to the population. And notice that the presence of a competitor will have a negative effect on the growth of the competition. So if x of t is, let's say, the fox population and y of t is coyotes, then you can see where this system, dx dt, equals, now look, see, a of x, that means it's growing exponentially according to the number of foxes, but going down, we're removing, the change in the fox population is affected negatively by the change in the coyote population. And similarly, the change in the coyote population, well, that's c times y, of course, but it's also minus d times x, so because that rate of change could be decreasing based on the size of the fox population. So that would be a very reasonable model. If we further make an assumption that each species grows logistically, okay, remember that from Unit 2, Lesson 2, then the populations grow according to dp dt equals p times b minus m times b. Recall that was what we used to generate the logistic function while shrinking from the competition. Then the model becomes a little bit more complicated. Here's the model. This is ax minus bx squared, which is really just this change in the fox population, and then there's subtracting the from the rate of change a factor of the coyote population. And similarly, coyote population grows according to this model, and then this would be minus some factor of the fox population. So there is a very complicated but very logical and maybe a little bit rough. Yeah, definitely rough. Yeah, definitely rough. Rough to solve, but I hope not too rough to understand, a system of non-linear, in this case, differential equations.